Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just to go through a quick demonstration or a quick kind of simple example of how Gauss's law applies. And what we're looking at here is this. I've got three surfaces here, and they're three identical surfaces. Here's one of them, and another one over here, and then here's the third one. And imagine these three surfaces. I've given them names: surface 1, surface 2, surface 3. And these three surfaces have the following charges inside of them. Now I put kind of a little key here in the upper right hand corner. So anything, circle with a plus is representing a charge of plus Q, some number. Circle with a subtraction here in blue is minus Q. An important fact is for this example, we're going to assume these are the same numerical values. Now again, just because you have a pair of point charges normally does not mean they're the same. They have the same charge, but for this example, let's assume they do. And what we're going to do here is we're going to try to calculate, pardon me here, I got a phone call. Back, sorry about that, folks. All right, so again, in this example, we have three surfaces, and there's a bunch of charge configurations within each of these three surfaces, some plus, some minus. We're going to assume that the numerical value Q is the same for all. So, for example, this is a charge plus Q. That might be, say, plus 2 coulombs. That means this one would be minus 2 coulombs and so forth. And again, that's just to make this example as simple as possible. And what we're going to do now is talk about, well, how could we maybe calculate the flux through each surface? And we're going to order the fluxes from largest to smallest. Which surface has the most flux, which one the least. So, first of all, flux, at first glance, we might say, well, electric flux, let me go back and do that in black. Electric flux, here's how it's calculated. It's basically field strength times area. However, the field needs to be perpendicular to the area. Now, this is always true, but this is not going to be a practical way to try to attack this problem, and here's why. If I look at even surface 1, if I were to draw some electric field vectors, if I draw an electric field vector right at this point, that vector would point, outward, away from this positive charge. If I pick another point, like maybe right here, again, that field vector, the electric field vector, due to this charge, is going to point to the right, kind of up and right, directly away from this charge. This electric field for sure will be a lot stronger than this one because it's so much closer. This distance is a lot less than this. Also notice here, if I draw some normal vectors, which I like to do in green, here the normal points maybe, roughly like this. Here it points maybe something like this. An important thing to recognize, well, two important things to recognize. One, the magnitude of the electric field is varying with location, depending on where I'm at. Second, the angle here between the electric field and the normal also is varying with location. That means that this is a very complex math problem. We're not going to be able to directly calculate the electric flux through each surface by direct computation like that. So, the other way we might think about handling it is through the idea of Gauss's law, because these are closed surfaces. Gauss's law, which says this: the total electric, let me use black. The total flux through any closed surface, which is the sum of all the EA cosine thetas on that surface, or again, I like to do this in a second form. I'm doing this in two different forms because some classes are algebra or trig based and some are calculus based. In an algebraic based class, I'd probably start here. In a calculus based class, I would say this: the total electric flux, which is the integral, which basically, which means sum over the entire surface of all the E dot dA on that surface. Both of these are equal to 4 pi kq. And again, these are saying the same thing. These two equations are saying the same thing. One is just, I would just say, a little stronger math format here. So depending on how you're thinking of flux, whether you're thinking about finite measurable areas and you're thinking about summing all the EA cosine thetas over those areas, or whether or not you're thinking about differential areas and integrating all the E dot dAs, in either case, that sum is equal to 4 pi kq. So when you look at this equation, the total flux equals this, which equals this. What I'm going to do is kind of skip right to here. So therefore, the total flux through any surface we can write as 4 pi k times the charge inside that surface. And I already talked about why we're not going to be able to directly calculate the flux through each surface. We're going to use basically this part of Gauss's law to answer these questions. So, make myself a little room. taking note that the total flux through each surface is 4 pi k times the charge inside the surface. That's going to allow me to quickly and easily write out the total flux through each surface. In surface 1, right, all we've got to charge here is plus q. So I'll call this flux 1. Flux through surface 1 is equal to 4 pi k q, because plus q is the charge inside that surface. This flux is positive. That's indicating it's an outward flux, that the electric field lines are leaving surface 1. Okay. All right. Taking a look at surface 2, by observation here, I've got 3 pluses, 3 plus q's, and 3 minus q's. So the net flux, the net charge inside surface 2 is 0. So the net flux through surface 2 also 0. Right? And again, that's because the charge inside here is 0. And again, the q inside is the net charge. For surface 3, I got 4 minus q's and 1 plus q. So the net charge inside of surface 3 is minus 3q. So the flux through surface 3 is going to be 4 pi k times minus 3q. Or we could simplify that to minus 12 pi kq. The minus sign's got a physical interpretation. It's no problem. It just means that the field lines are coming into the surface. That's an inward flux, a net inward flux instead of a net outward flux. Now, as far as ranking these from lowest to highest, now we're not ranking vectors. The minus sign, the physical interpretation, is just the inward flux versus outward. So I would say, obviously, surface 2 has the least amount of flux. Surface 1 has a flux of 4 pi kq. That flux is outward. That would be the second least or amount of flux. And then the largest amount of flux, this guy. Surface 3 has the largest amount of flux, and I would say that amount of flux is 12 pi kq. Again, the minus sign just means inward. So most flux through surface 3 because it has the most net charge. Next most, surface 1, because it has the next most amount of charge, and then surface 2 here does not have a net flux at all. So this is just meant to be kind of a quick example here of Gauss's law and one way to apply it, and I'm going to start some more mathematical examples next. Have a great day.